Okay, let's get my tablet connected.
Okay, so Alice is all the time. So let's go over homework. I think we'll have. How much have you done, Alice?
Okay, let's get started. First, I sent out some notices yesterday about final exam logistics. I'm going to give you a wide time slot on Monday, the 7th. I'm not planning on it taking 7 hours. I'm planning for it to take roughly 2, but people have other things going on that day. I've gotten a lot of requests to reschedule the exam because people have 2 exams that day. The problem is that almost any day of the week that we might pick, there are going to be a lot of people with 2 exams on that day. So I'm going to follow university policy and say that if you have 3 exams on that day, you can move one of them, and that one can be mine if you want. But unless I got a unanimous agreement on another day, university policy really doesn't let me move the exam. I could just give everyone 2 days, but it's designed to take 2 hours. So I'd like to see most people take it on Monday if possible, and then whoever needs to, because they have 3 exams, just let me know. I can verify your class schedule real easily, and then we'll set something up for Tuesday. Any questions? Okay, so last time we were talking about Bessel functions. They were solutions to this equation.
You know, like we can alternate between the 2 things. Yeah. And I she's not really understand the
and that comes from the wave equation. And we talked about the different kinds of solutions to that. We wrote down a series and derived something and verified this convergent. And then I said, I didn't prove it. To prove it is quite tedious. And so I'm going to, I don't know, some people might think that what I'm doing right now is kind of bad. I'm asserting a lot of things without proof, but we're introducing a class of functions. And the first time you learn things about sinusoids, did someone rigorously prove to you that they oscillate? Or did they just, you know, show you the circle and show you how it goes around and then make a graph? So I'm trying to give you intuition for this class of functions that you'll encounter occasionally. If you have a project where you need to make very in-depth use of them, then I'm showing you just enough steps in the derivation that you can go in and learn the rest. But one of the key properties we learned is that JM goes to a phase-shifted sinusoid, or a phase-shifted cosine of KR minus some phase, and that phase shift depends on the order of the Bessel function. And YM goes to sine of KR minus a phase over square root of KR. And I argued that this is plausible because it means that if our wave, like if this was an electric field, well, the intensity is proportional to E squared, which is proportional to JM squared. So that's going to be proportional to cosine squared KR minus a phase over KR. And if we integrate that, if we think of this as a wave spreading out in 2D, a ripple, and you could say, but we live in a 3-dimensional universe, but well, waves on water electrons confined into a single sheet. That actually happens a lot in semiconductor devices. You confine electrons in a plane. There's a number of scenarios where waves are confined in 2D. So if we do that, then we're going to be integrating around here. So the integral of I times R d phi, you could say Y R d phi. Well, this little segment of the boundary is R d phi. That's going to be proportional to the integral of a cosine squared over KR times R d phi. So we're going to get something that's independent of R. That's an asymptotic property of the Bessel function. Any questions on that? Well, that just proves that the amount of energy spreading out is independent. The amount of energy on any given surface is independent of R in the limit of large R. I'm going to have you prove on the final problem set that that holds true, not just for large R, where we can make that approximation, but for any R, using a more detailed calculation from wave theory. But what I want you to keep in mind is that Bessel functions, as strange as they look, have properties that fit quite nicely with waves. And now I want to talk about another property of Bessel functions. If you think back to Monday, I made some graphs of Bessel functions, and I showed you that whereas some of them oscillate and slowly decay, others can either decay exponentially or increase exponentially. And I made the heuristic argument that, well, these Bessel functions behave approximately like sinusoids, and sinusoids are made out of complex exponentials. So with a change of variables, we should be able to go from a complex exponential to a real exponential, and real exponentials don't oscillate, they either blow up or decay. And now I want to give you a physics context where that matters. So let's start by talking about total internal reflection of light. We all know Snell's law. We've got light, it's in a medium with index n1, it goes to a medium with index n2. In this medium, it makes an angle θ1. In that angle, it makes an angle θ2 with the normal. And n1 sine θ1 equals n2 sine θ2. Now I could think of a wave as being characterized by its k vector, okay? K is going to point in the direction that the wave is traveling. And K has a length. I'm going to call that length K naught. Well, actually, the length of that wave is going to be K naught times N, because it depends on the medium. Because that length, the length of the K vector is 2 pi over the wavelength, or 2 pi divided by the wavelength in vacuum over N. Because in high index media, the wavelength of a wave gets smaller. And 1 over N is N, so we get 2 pi N over lambda naught, or N K naught. So if I multiply both sides of Snell's law by K naught, what I effectively get is, well, I've got the length of K multiplied by a trig function. The length of a vector multiplied by a trig function is usually a component of the vector. And you tell me, is this going to be the horizontal component or the vertical component? Anyone? Anyone? Bueller?
Horizontal.
It's going to be the horizontal component. So I've got the Kx in medium 1 equals Kx in medium 2. All right, so when the wave goes from one medium to another, Kx doesn't change. But the length of K does change. So if Kx doesn't change, Ky must change. And that's how it changes direction. That's why it refracts. That's why besides changing length, it changes direction. Now let's think about the implications of that. That means that Kx squared plus Ky squared equals n squared K naught squared, or Ky is the square root of n squared K naught squared minus Kx squared. All right, well, in medium 2, Ky in medium 2 will be the square root of n2 squared K naught squared minus n2 squared K naught squared sine squared theta 2. Nothing profound so far, except that n2 sine theta 2, I'm going to pull out the K naught. N2 sine theta 2 is n1 sine theta 1. Let's say that n1 is bigger than n2. If n1 is bigger than n2, then we have a problem here. Depending on the value of theta 1, we could get that this is bigger than this, which means that we could get a negative number underneath the square root. If we get a negative number underneath the square root, then the square root of that is going to be imaginary. And the convention is to call that I kappa if n1 sine theta 1 is greater than n2. Physically, what that means is, let's see, sine theta 2 is n1 sine theta 1 over n2. N1 sine theta 1 is bigger than n2, so this is bigger than 1. I don't know of any angle in our real three-dimensional Euclidean universe that can have a sine bigger than 1. So this is geometrically impossible. This is not just physically impossible. This is geometrically impossible, which means that we can't have a wave traveling in here. Any questions on what I'm saying? So what we've got here is that if we have total internal reflection, phenomenon that you learned about in freshman or sophomore physics, depending on where you took it, in what order they did the topics. And some places put waves early in the curriculum, some put it late. But when you have total internal reflection, the wave decays exponentially. It's not traveling freely. It's decaying exponentially. That's what this means, because we get that E in medium 2 is, well, right, it is proportional to e to the I kx times x. That thing is still the same. Kx is still real, so we get I kx times x, e to the I times I kappa y. And let's see, I times I is -1, so we get e to the minus kappa y, e to the I kx times x. So we get something that if you just look along the x direction, you just ask, well, what's the value here, and what's the value there, and what's the value there, and what's the value there, you see something going up and down. But if we take measurements going further out along the y-axis, you ask, what's the value here, what's the value there, what's the value there, what's the value there, you see something that's decaying. Now, of course, if I'm way up here, I still get something, it's very tiny, but there's something. And then over here, there's something, and it's still tiny, but it's oscillating. So if I only look along this direction, it's oscillating because everything is proportional to e to the I kxx. But it's a very tiny thing, and it gets smaller as I go further from the interface. Any questions at all, whether on the math of that or the physics or the meaning or whatever? Speak now or get ready for Bessel functions. Well, there is a very, very, very practical situation where this shows up, and you're using it right now. It's the internet, because even if you're on a mobile device, if you're on a network at home, the odds are good that your router is probably not directly connected to fiber, but is probably connected to a cable, to a metal cable. But that metal cable is connected to something not too far away that's connected to an optical fiber. And if you're on a cell phone, again, you're connected to some radio waves, but those radio waves are going to some sort of transmitter that is almost certainly connected to a fiber optic cable, right? And so in a fiber optic cable, we've got large N1, small n2, small n2, or a cross-sectional view. All right, the internet is quite literally a series of tubes. That senator from Alaska, Ted Stevens, was right. Nobody remembers what his position was on the legislation. Nobody cares. We just remember that he was giving a speech about how the internet is a series of tubes, and he was right. And the series of tubes is based on optical fibers. And so we have to be able to solve the wave equation for something in a cylinder. Now, I'm not going to do all the details of it today because there are a lot of subtleties about the polarization and the boundary conditions that really require a large amount of prelude material in an optics class. But basically, you're going to have Bessel functions because we're solving the wave equation in cylindrical coordinates. Now, inside, the only thing that the wave can be is some amplitude times Jm of N1 K naught R times e to the I m phi. And you could ask, well, don't we have two linearly independent solutions to the wave equation? Yes, we do. But one of those linearly independent solutions, Ym, blows up at the origin. So we can't have anything that blows up at the origin. So it's got to be this. Now, out here, we've got a decaying wave. Okay? What that means is if we go back to the fundamentals of the wave equation, d squared e by dr squared plus 1 over r dE dr minus m squared over r squared plus, and now I got to be very careful here. I should really be taking into account the z dependence coming up out of the page. It should also have an e to the I kz z and then e to the minus I omega t. All right. So I should have that, and that should be multiplied by e, and that should be multiplied by e. And all of that should be equal to n squared over c squared times minus omega squared e, because that's from the time derivative. All right. Well, omega squared over c squared is k naught squared. Just so I don't have to carry around quite as many symbols. So I put all this together, d squared e by dr squared plus 1 over r dE dr minus m squared E over R plus n squared K naught squared minus K Z squared E. Now, normally, this is smaller than n K naught. KZ, the component of the K vector coming out of the page, is playing the same role that KX played up here, all right? It's got a different name, but it's the component of the K vector that's along the interface. And here, KZ is the K component that's along the interface. And if we have a very high refractive index inside the fiber, then KZ could be quite big inside the fiber. The problem is we've got a low index outside the fiber, okay? If we've got a low index outside the fiber, then this could be negative outside. So outside, I'm going to write this entire thing as minus kappa squared. And so I get d squared E by dr squared plus 1 over r dE dr minus m squared E over r minus kappa squared E. And all of that, oh, that should be r squared, my bad. All of that is equal to 0. This is called the modified Bessel equation. It's modified because instead of having the plus k squared that we had before, now we've got minus k squared. And those are the solutions that wind up having the exponentially decaying behavior instead of the oscillating behavior. So outside we get B somebody decided to call these capital K, and that's totally different from kappa, not my idea. And then here's what they do. A solution to the wave equation only works if E and its derivative are continuous. So we say that E of big R, the fiber radius, I'll call it, which means that A JM of N1 K K naught R equals B KM of kappa R, and kappa is equal to the square root of N2 squared K naught squared minus KZ squared, or if you want to think of it in terms of frequency, N2 squared omega squared over C squared minus KZ squared. All right, that's what E is equal to at the interface. And then we also have to set the derivative equal on both sides. So when we take the derivative, we're going to get N1, we need dE dr, evaluated at R, N1 K naught. Hang on, someone's at my door. I'm in a meeting, is this urgent? Okay, crap. All right, everyone, they're about to cut the tree. They're about to cut a tree next to my car, and we didn't get the notice. And I feel really terrible about this, but I will be back in a few minutes. I'm sorry. All right, these are the things that happen when you're working from home. Where was I? Okay. So We set up these expressions for waves in a fiber optic cable. We said the electric field has to be continuous and its derivative has to be continuous. Now you're wondering, what are the derivatives of Bessel functions? And the answer is that the derivatives of Bessel functions are messy things that no one ever memorizes unless they use them every day, and then they look them up. But the main thing, oops, I left out an A. The main thing you should notice is I've got two equations and two unknowns. It looks so great, except that if I take the ratio of these equations, the A's cancel, the B's cancel. I'm left with N1 K naught Jm prime of N1 K naught R equals kappa Km prime of kappa R. Well, there's no guarantee that that equation is satisfied. That equation is only satisfied for certain values of K naught and kappa. I could rewrite that as N1 omega over C Jm prime. Oops, that should have been over Jm, and that should have been over Km. Km prime of all that over Km of all that. That's a messy, dirty equation. It isn't always satisfied. It's only satisfied for certain combinations of omega and Kz. Only certain omega Kz combos will satisfy it. Now, studying those combos, studying their properties and what the physical implications are, that's for an optics class. What I want you to take away here is that this is why that tremendous zoo of Bessel functions matters. That's why we have all of these many different kinds of Bessel functions, including the modified Bessel functions that for some reason a lot of the undergraduate textbooks give short shrift to. Of all the things that the undergraduate textbooks, this one included, could focus on, they tend to focus on the details of writing out that series. But in fact, solving equations like this with modified Bessel functions is what people tend to do. It's a specialized topic. What you need to know in a general math methods class is that Bessel functions exist. Here are their basic properties. If you find yourself designing a fiber optic cable, then you would basically make a graph of Jm prime over Jm for different values of omega or K naught and Kz, and set that, and then also make a graph of kappa m prime of Km prime of kappa R over Km for certain values of omega and Kz, and see where those graphs intersect. And wherever those graphs intersect, that is where you have a physically valid solution for that fiber. Any questions? Okay, so that's the, those are the details of one application. Now that's a very elaborate application. I want to go to a somewhat different, simpler application, not as practical, But this is the one that I'll actually put on the homework because it's kind of a warm up to doing more sophisticated things with Bessel functions down the road. One question we could ask is, let's say we just want to solve the wave equation, not inside of a fiber where you could have a field inside and then some of that field leaks out. So if we plot E versus R, you've got something that's oscillating in here and then it just decays out there. Not that, because that field never exactly equals zero. It just gets smaller and smaller and smaller as you go out there. What if instead we have a metal tube? We can find a wave inside a metal tube, and then we can say that E equals 0. At the boundary. And let's make this even simpler. Let's say that KZ equals 0 so that we don't have to worry about that. If you really want to worry about that, we could always say, well, d squared E by dr squared plus 1 over r dE dr minus m squared over r squared plus k naught squared minus kz squared E equals 0. But all that's really going to matter here is just k squared. And whether that k squared is k naught squared minus 0 or k naught squared minus some non-zero kz squared, we don't care. The only thing we know is that this has to equal 0 at the boundary. All right. E equals 0 times Jm of Kr. That's what the solution has to be. Are we done? Oh, wait, there should also be an e to the I m phi, and if you want an e to the minus I omega t and an e to the I k z z. So we did those technicalities. Are we done? Well, not quite, because on the one hand, yes, we know the solution has to be this because we don't have the modified Bessel equation with that minus kappa squared. We've got the usual Bessel equation. This is positive. So we've only got two solutions, two Bessel functions, the Jm of the first kind and the Ym of the second kind. We don't have to worry about the Km that isn't even in this textbook. But we know that we can't have the Ym. Why can't we have the Ym here?
It blows up at the origin.
Yep, Ym blows up. So that's not allowed. Okay, now are we done? Now that we've ruled out Ym, is there anything else we have to take into account? Is there any physics? Is there anything special that happens out here at big R?
E has to be equal to 0 at that point.
E has to equal 0, okay? Jm of k big R equals 0. So we can't just put in any old value of k, all right? If we just put in any old value of k, then we might get a problem. We have to put in special values of k. Kr has to be equal to alpha mn, which is the nth 0 of Jm. You say, why the nth 0? Well, because if I switch to Mathematica, if if I switch to Mathematica, somehow my Mathematica screen has gone away and my chat screen has overtaken it. And my Mathematica screen is showing on my other device, but not, okay, there it is. So if I just look at a plot of JM, it has many zeros. So here's a plot where I say, all right, I'm going to consider J0. That just means I'm going to have a circular Bessel function. Sorry, that just means I'm going to have a circularly symmetric case. I'm not going to have any dependence on phi. And I'm going to go out to the 5th zero. I don't have to. I could go out just to the 1st zero. It's going to take a minute to plot that. Right? I can have something that just goes out to the 1st zero. Or I could say, you know what, I want to look at a slightly higher frequency. I could go out to the 2nd zero. And for some reason, it takes a long time to render these plots. And I spent some time Googling and looking at Stack Exchange to see if there were easier ways to do this, but these were the fastest commands I could find. So we could go out there and you could say, wait, how does that have only two, how does that have 2 zeros? Well, it's got a peak, it goes down, and it's not necessarily obvious from an angled view, but from a side view, you can see that it's equal to 0 here, which means it's less than 0 there. So it goes down to 0, keeps going down. You can see it if we look at it from the side, then goes back up. That would be a physically valid solution. Can you tell me how we could deduce that this must be a higher frequency? I can think of at least 2 ways, one more physical, one more mathematical. One more physical way is that it wiggles a lot. Whenever a wave wiggles a lot, it must have a higher frequency. It's wiggling more than the previous case. It's not wiggling as much as some of the higher cases. Like if I went out to here, m equals 9. And you could say to me, wait, you're setting k equal to 0, not kr. Yeah, but I'm plotting it out. I'm saying that the radius is 1 in our units. Sometime in the next hour, it will show us a case with a lot of wiggle. All right, here's a case with a lot of wiggle. We look at it from top down, and we can see many peaks and troughs. And it starts to look a little bit like ripples on water, right? We don't have to just look at the m equals 0 modes. Let's look at the m equals 1 modes. And let's do 3. Mathematica has a built-in function that will tell you what is the first 0 of JM, what is the second 0 of JM, what is the third 0, so that you don't have to make a graph, zoom in, then maybe zoom in again to get another decimal place. It'll just tell you, oh, the first 0 is at 2.4 whatever. The second 0 is at 5.5 whatever. Okay, now that's a really funky looking wave, because that's a wave that has 3 zeros going out, but it's also proportional to cosine of phi. Ignore these. These are x and y coordinates in the polar plot. They don't matter. This is what matters. This is how high up or down it is. The height up or down is cosine of phi. Let's go out to a whole bunch of ripples. These things, that just looks kind of weird, but if you go out to many more ripples, it starts to make a bit more physical sense. Okay, so now what we've got is we've got something that ripples outward, that ripples several times as we go outward. If we go from the center out, we can count many ups and downs. It's also proportional to cosine of 2 phi, which means out here, when I go out from the origin, I hit a peak right there. I hit a peak here and here. But then up here, if I go out from the origin, I hit a trough. So wherever I'm hitting peaks going one way, peak here, trough there, peak here, trough there, peak here, trough there, peak here, trough there. Because I'm multiplying by cosine of phi, depending on the angle, that cosine, cosine of 2 phi, depending on the angle, that cosine could be positive or negative. And that shows up in the structure here. If I wanted to go out to m equals 3, and plot it, then I'm going to get a hexagonal pattern. And sure enough, we get a hexagonal pattern. These things are beautiful just to look at. I swear that that's half of the reason why people study complicated wave patterns, is for the pretty pictures. Looking at it from a side view is also kind of spectacular. Any questions so far? This beautiful picture and nobody wants to ask a question about it?
Is that,
Yeah.
is the symmetry due to like your M? If you change the M, would you get different numbers? Could you get like 4 or 5 different lines that you
Yep.
looked at?
Yep. Well, you always get twice as many lines as you get 2 m lines. Like when I had m equals 2. Well, no, you get 2m. You get twice as many segments. M lines, 2m segments. Yeah. So m is absolutely related to the symmetry. So KR is equal to alpha mn. So K is alpha mn over R. So omega is equal to C alpha mn over R. Very narrow tubes hold waves with very short wavelengths, high frequency. Wide tubes can hold waves with long wavelengths, low frequency. That's the relationship here. So if you were to, in principle, if you were to solve the wave equation for some kind of membrane, so you have some circular membrane and you know what speed of sound is on that circular membrane, you could solve the wave equation. You could say, all right, I'm going to look at all of the different alpha mn values that will give me modes. That's what these solutions are usually called. They're called modes because they're literally a mode of vibration. They're one way that the thing could vibrate. I could look at all of the possible alpha mn values. And then I could just hit that thing and it would start vibrating. And a drum doesn't vibrate very long as far as human perception is concerned, but it might vibrate for, a second, which for kilohertz sound is thousands of cycles. So I could hit it and I could record that sound, and then I could feed that sound to a spectrum analyzer, which is just taking a Fourier transform, and I could Fourier transform it, and I would get a bunch of spikes, and each of these spikes would be C alpha MN over R. Any questions? Well, what do we know about distinct solutions to equations? Whenever we've solved problems like, say, the problem of solutions to the wave equation, where we got our different spherical harmonics. What do we know about the spherical harmonics? What's a property that they have if I were to try to see how much one of them overlaps the other?
They're all orthogonal.
They're all orthogonal. It turns out that if you set things up carefully, if you define your inner product very carefully, then certain kinds of Bessel functions are orthogonal to each other. Now, if I just make the statement Bessel functions are orthogonal to each other, that's generally not true. If I were to just write down the integral from A to B of Jm1 of K1R, Jm2 of K2R dr, that's probably not 0. Okay, so we can't just define it that way. But these modes, if you think about it, I didn't just define these modes any old way. I gave them a physical condition, E equals 0 at the boundary. So if I limit my attention to modes that are equal to 0 at R equals big R, and so I only look at, say, this mode and this mode and this one, and that one, those are equal. Those are orthogonal, and we're going to prove it because the technique that we use to prove it, I've been avoiding a lot of Bessel function identities. I'm not going to teach you how to prove a fact that's useful for one specific property of one kind of Bessel function. But these orthogonality relationships show up in a lot of places, and we can use the same technique for all of them. So I am going to prove to you that the integral from 0 to R of Jm of alpha m n over R times little r, that's just saying that K is equal to alpha m n over R times Jm of alpha m n prime over big R times R, R dr, that is equal to 0 if n is not equal to n prime. Now let's think about physically or geometrically what it means to write K in that form. That means that if R equals big R, alpha m n R over big R equals, well, let's see, I got little r over big R, that would be 1. That would be alpha mn. That's a 0 of Jm. That's a place where Jm equals 0. So what I'm saying here is that I've written these out in such a way that these two functions are different from each other in many respects. They've got different K values. One of them might be this with, just a single node, and this one might wiggle a whole bunch. One of them wiggles more than the other, but they both equal 0 at the end. That's absolutely crucial. If someone gives you an orthogonality relationship for Bessel functions and doesn't specify that they're both 0 at the end, they're almost certainly wrong. I say almost certainly rather than certainly because you can always, with a big enough zoo of functions, find some weird case. Also, anybody guess why we've got an RDR in that integral? Bessel functions are solutions to the wave equation in cylindrical coordinates. And so this is part of a bigger integral in cylindrical coordinates. When you integrate in cylindrical coordinates, you always have an RDR. This is really part of an integral from phi equals 0 to 2 pi, little r equals 0 to big R, e to the I, m1 phi, e to the minus I, m2 phi, jm1 of k1 r, jm2 of k2 r, which would just be alpha mn if you prefer, alpha m1 n r over big R, alpha mn 2 prime over r. If you want to do it that way, r dr d phi. But what do we know about that integral over phi? This is the part of the integrand that depends on phi. What do we know about integrating that over phi?
It's 0 less
The
than
answer
1
to
equals-
next Friday's follow-up assignment. What do we know about that integral over phi?
It's 0 unless m1 equals m2.
If m1 is not equal to m2. Yeah. And this is why people almost never prove orthogonality relationships for Bessel functions of different order. We rarely care about J2 being orthogonal to J3 because usually when we encounter J2, it's multiplied by e to the 2i phi. And when we encounter J3, it's usually multiplied by e to the 3i phi. And so those are already guaranteed to be orthogonal just because of their phi dependence. We normally only care about the case where m1 equals m2. And so I'm going to, now that I've motivated it, now that I've established that I don't really have a good physical reason to care about these orthogonality relationships when the m's are different, now without further ado, let's prove it. We will prove it by writing the Bessel equation in the following form. And now I have to check my notes because there are about a gazillion ways to do this wrong. Well, I'll start off writing it in the most conventional way, and then I'll start off doing it conventionally. All right, so this should really be a function of K1R. And now I'm going to divide both sides, not by r squared, which is what we usually do, but just by r. Okay? And when I've just got the r, I could rewrite this entire thing as, I could write this side as d by dr of r djm by dr minus m squared jm over r equals minus k1 squared r jm K1R. Right? That would be a perfectly valid way of writing it. And it's going to turn out to be a useful way of writing it because in a little bit, we're going to do some integration by parts. And then I can ask, what is the integral from 0 to big R of R Jm of K1 R Jm of K2 R. And at this point, I am not yet making any assumptions about those K values. I will in a little bit. I will eventually assume that those K values are chosen to make it 0 there, but for now we're not making that assumption. Well, that's just got to be the integral of, and if you want, I could divide by minus 1 over K1 squared. Let's just do that right now. We're going to get a result that's similar to what we did with Legendre polynomials, and then next week we'll generalize it. So we're going to get -1 over K1 squared integral of Jm of K2 R d by dr of R dJm dr K1 R dr plus 1 over K1 squared m squared integral of Jm of K1 R Jm of K2 R over R dr. And all of this should be from 0 to big R. Now, one thing we should notice is that the second term doesn't really depend on the fact that I wrote out Jm of K1R one way. I wrote it out in terms of all those derivatives and everything. And I just wrote Jm of K2R on its own. This term would be the same if I swap them. But that would change, okay? Because I could have also said, hey, minus 1 over K2 squared times that derivative, d by dr of R dJm dr let's not do that last one, minus m squared Jm of K2R over R. All of that is equal to R Jm of K2R, and then I can multiply by Jm of K1R, both sides. All right, and then I integrate and what would I get? I would get a term that looks like this with some things swapped, and I would get this term. All right, except that I would have the K1 swapped with K2. Now, changing this, we ought to get the same result because both ways we're integrating R Jm of K1 times Jm of K2, right? We ought to get the same thing, except that we've changed not the form of this term, not the integrand in that term, but the prefactor outside. You could say, well, but we also changed the top term. But I'm going to prove that the top term here, this one doesn't change. Because if we just attack that term, here's what we get. We get minus 1 over K1 squared. Now we integrate by parts. UV evaluated from 0 to R minus the integral from 0 to R of V du. And we'll say that U is equal to Jm K2R, and dV is the derivative of R dJm dr of K1R. Okay, well, that's U in dV. So du is the derivative of that. And V, well, if V was the derivative of all of this, if dV was the derivative of all that times dr, then V is just R dJm dr evaluated at K1R. So let's put all that together. We get -1 over K1 squared times R Jm of K2R d by dr of R Jm of K1R. It's looking really ugly. Okay. Any questions on how I got there? Speak now, or we start manipulating this and simplifying it. Okay, let's try to make some of this go away. At the lower bound, at R equals 0, do you see anything in here that's equal to 0? That's 0 at the lower bound. So right away, we know that we can at least get rid of something. Now, evaluating at the upper bound, let's see, Jm of K2R, if we assume that K2 times big R is one of the Bessel function zeros. It's one of the zeros of Jm. It might be the first zero of Jm, it might be the 15 millionth zero of Jm, but it's a zero of Jm. If it's a zero of Jm, then guess what? This product is 0 at the upper bound. Obviously, little r isn't 0, this derivative isn't 0, there's any number of things that aren't 0, but this is. So all of that goes away. And we're left with this expression. And this expression would be the same if we swapped K1 and K2. So what we ultimately get is that the integral from 0 to big R of Jm of K1R, Jm of K2R, R dr is equal to -1 over K1 squared times 2 integrals. This integral and this integral. But it's also equal to -1 over K2 squared times the same 2 integrals. Well, I don't know about you, but I only know of one number which will give me the same result, whether I multiply it by 3 or 4 or 5 or 6 or anything else. And that number is 0. So those 2 integrals must be 0. And hence we have proved the orthogonality of the Bessel functions if, and this is a very important if they have the same m and the k's are chosen so that there's 0 at the edge. In other words, I'm proving the orthogonality of, say, if I were to do something other than J0. I'm proving the orthogonality of this and this, all right? I'm not proving the orthogonality of any two Bessel functions over any range. I'm proving the orthogonality of any two Bessel functions that have the same order, which means that they're part of something that has the same angular dependence in the wave equation and has zeros at the edge. Any questions? Well, there's only one thing left to do when you've got some orthogonal functions, and that's write down a series. I can say that f of r is equal to the sum from n equals 1 to infinity of Jm of alpha mn r over big R times Cmn. These CMNs are coefficients, right? So I could take some function of R and I could evaluate it on a range. I could approximate, not over all of space, not over all values of R, just from R equals 0 to big R. I could approximate it with whatever set of Bessel functions I want. I could approximate with J0 value with different K's in there, J1, J2, J3, J whatever. Okay, I could approximate whatever ones I want. You could say, well, which ones would you choose to use? Which ones should we want to use? And my answer is, well, are we trying to solve some problem where a wave has nice cylindrical symmetry about the axis? Are we trying to solve some problem where the wave has a cosine of phi term, or a cosine phi factor, so that in half of space it's positive and half it's negative? Are we trying to solve something with a cosine or sine of 2 phi, something with a cosine or sine of 3 phi? That's going to tell me which Jm I want to use. But whichever Jm I want to use, I can write my function as a series. And then we could get the coefficients in the way that we always do. We could integrate, we take an inner product. So we integrate from 0 to R, f of R, Jm of alpha m n little r over big R, r dr. This is one type of inner product. This is the inner product that we need. This is the appropriate definition of an inner product for these kinds of functions. And you may be a little bit worried that we have multiple kinds of inner products, because for three-dimensional vectors in Euclidean space, we just have one kind of inner product, but that's one kind of space. That's one mathematical setting. Well, that's going to be the sum from n equals 1 to infinity of the integral, n prime of Jm of alpha m n prime over big R, R, Jm of alpha m n little r over big R, R dr. And there should be a coefficient in there. And what do we know about most of these integrals?
They're going to go to 0.
They're all going to go to 0 unless n prime equals n. And so we're left with Cmn integral from 0 to big R, Jm squared of alpha mn over big R times R dr. And this is something we can look up in a table. The details of this don't matter. They matter, but the details of this are not a generalizable skill. The details of this apply to this category of functions, whereas everything that we did to prove the orthogonality works for Bessel functions, Legendre functions, Hermite functions, Laguerre functions, and all of the other things that you'll need in quantum mechanics. That just turns out to be oops, I don't need that square there. So C, and what you should take away is that we have yet another type of series that we can use. We would only use it if we're really interested in solving a wave equation in cylindrical coordinates. No one would ever say for masochistic pleasure, hey, we've got this problem that doesn't have any cylindrical symmetry or anything even close to cylindrical symmetry, and it doesn't involve wave equations. But yeah, let's do one of these Bessel series. No one would ever say that. Well, maybe someone would. There's got to be some weird case where even though they don't have waves, they nonetheless get a similar equation. But in 99.99% of all cases, you would only do that for the wave equation. What I want you to take away is that for every type of orthogonal function that we can think of, every type of orthogonal function that we will use, you can break a function up into different components, each of which corresponds to one of those orthogonal functions. So you could take a function, break it up into sines and cosines if it's periodic and that's what's most appropriate, or break it up into an infinite spectrum of sines and cosines with a Fourier transform, or break it up into Legendre polynomials like we did last week, or break it up into Bessel functions, and it'll work. And so this is a pattern that we've seen again and again. Next week, I'm going to talk about some of the structure underlying that. Instead of just saying, okay, well, here's the Bessel equation, or here's the Bessel function with its particular properties. I'm going to prove this for some arbitrary set of orthogonal functions satisfying some arbitrary differential equation and show you how all of that works together. With that, have a good weekend. Have a happy Thanksgiving, as happy as it can be under the circumstances. And I will try to catch up on some grading. You should notice that your last problem set is much shorter than usual. Have a good day.
Thank you, Dr. Small.
You're welcome. Okay. Yeah, I couldn't call you, so I had to go do it in the middle of class.
I'm so sorry. That was so hard.
I got through it. Somebody knocked on the door in the middle of class They kept saying hello. And I'm like, I'm in a meeting. Is this important? They said, yeah, it's important. They're about to cut the trees. If you care about your car, you gotta move it.